Instead of posting a video this weekend, I decided to just cover what I wanted to cover real quickly today. There's one thing I wanted us to see for your homework, which is correspondence analysis. So I'm going to show you an example in class today. And then with the rest of the week, we're going to move on to a new topic. Which will be statistical inference. So far, we have been getting familiar with R and exploratory techniques. So exploratory data analysis, just looking at data, making pictures and things like that. We'll finish today the three main kind of unsupervised techniques that I'm recommending to you: principal components, cluster analysis, and correspondence analysis. Principal components, remember, is a technique for taking a collection of numerical variables and representing them in a lower dimensional space that helps us to see the structural elements of the data, or at least of the numerical variables. Correspondence analysis is a lot like that, except it's for categorical variables. So if you think about what principal components does, it takes a covariance matrix and it gets eigenvalues and eigenvectors. That's what it does. If we have categorical variables, how do you do that? So let me show you a data set. It's not exactly a biostatistics data set, but it's useful for illustrating this. So under data, there's a new data set called DIY. So let's download and play with this for a moment. I've also got, under scripts, a DIY.R file. And this file has the code that you can use, you can adapt for doing correspondence analysis in your homework. And while I'm here, I'm going to go ahead and download some PowerPoint slides I posted that we'll use this week. So under Notes, I'm going to get this guy called Simulation-Based Inference. Okay. The file is actually called chapter5.pdf, but it's from a different class, so it's not our chapter 5. On eCampus, it's called Simulation-Based Inference. When you download it, it'll be called chapter 5, so you could rename it if you want. Okay, so let's take a look at the data, the DIY data. I'll go into my scripts and open up the DIY.R file. Okay. Back in R, I've got my working directory in the right place. So I'm going to just read in the data. So what do we have? We have 1,601 observations and 5 variables. Here's a peek at the data set itself, the first 6 rows. So here are our 5 variables. This is do-it-yourself data. Think about, suppose you work at Home Depot and you have access to the huge database of customers and characteristics of the customers. So here's a bunch of customers, and for each of them, we know some information. What kind of work do they do? Is it, let's do table work. Are you a skilled laborer, an unskilled laborer, or other? Don't know what all other captures, but there's 3 levels to this categorical variable of the nature of work. What about tenure? Tenure refers to, do you own or do you rent your home? DIY is a variable that was constructed based on purchase history. Let's stick with the Home Depot scenario. When you buy certain types of products, it makes you look like a do-it-yourselfer, or maybe not. So if I go into Home Depot and buy a bunch of nails and a hammer and a table saw, I might get labeled as a DIY person. So if I work at Home Depot, it'd be nice to be able to identify people who are like this, because then you could blast them with marketing specific to their interests. You appear to be the type of person who likes to work on their home. Perhaps you'd be interested in this special offer. So we have DIY. We also have an age variable. So each customer is either 30 or younger, or above 30 but less than or equal to 45, or above 45 years old. And finally, the type variable, which is the type of home. Are you in an apartment or are you in a house? Okay, so you work at Home Depot. You have this data set that your boss gave you, 1,601 customer records, and we would like to explore it. What kind of patterns, relationships, structure are there in these data, categorical data? If these were numerical numbers, we could do PCA and ask, what's the nature of the story behind our numbers? We're going to do something like that, but it's a specialized technique that's been around for a long time. It's analogous to PCA. In fact, it is PCA on a specially constructed numerical matrix. So I can't do matrix algebra on a bunch of categorical variables. They're, text strings, but you can tabulate or cross-tabulate all the combinations of these. So how many times was there skilled, rent, yes, 0 to 30, and apartment? Tabulate that. And how many times was there skilled, own, yes, 0 to 30, and so on. So you could imagine a big array of counts, frequencies. That's numbers. Turns out that they're of the right, have the right properties for us to actually apply eigenvectors and eigenvalues. So if you have a matrix of information, eigenvalue, eigenvector extracts the essence of it in some sense. So behind the scenes, we're not going to go into all the detail of it, but behind the scenes, what this algorithm is going to do is cross-tabulate these categorical variables and then do eigenvalue, eigenvector stuff on the resulting matrix. Okay, so let me show you what that gives us. To do multiple correspondence analysis, there's multiple ways to do it in R. I'm recommending you use the CA package. If you haven't already, let me see if we've got it here. Library, CA. Okay, there's no package called CA, and this may be a problem. Let's see. When you get a message, so libraries in R, these are collections of custom functionality to do some specific task, but they don't come with the base R installation. R has lots and lots of stuff in it when you just download it, but one of its values is that it has all these packages that you can get additional functionality through. The function I want to use is in this package called CA, but we don't have it on this computer yet, so we need to install the package. I don't remember if I've gone through this in the class or not. The R cookbook has instructions on this, but I'm going to click on Packages and say Install Packages. You can either have a package installed or not. If it is installed, then you can load it in and access all of its functions. It's not installed on this computer yet, so I clicked on Install Packages. I'll go find a local server to download from. Click OK, and then it pops up the list of all packages that are available. Lots of them. So I'm going to scroll, I'm going to type in CA. It's not going to let me do that, so I'm just going to scroll and locate manually CA. So there it is right there. Click OK, cross your fingers, because this computer acts weird sometimes. Okay, it should download and give you that. Successfully unpacked, and everything looks good. So that's good. Now let's see if we can library it in. Good. Warning message, don't worry about it. It's just saying this package was built under a previous version. Okay. And then here's how you do the correspondence analysis. For our purposes, I want you to call the function, look at the output, and make the picture. So here is calling the function and looking at the output. Here's the output. What we get is PCA-like output. In particular, we have different dimensions or directions that were obtained. And we have percentage of information explained by each of, in this case, 3 different directions or dimensions. So, almost 3/4 of the information content in our collection of categorical variables can be explained in one direction. Just like in PCA, we like to take our numerical variables and boil them down to one direction that is most informative, that most captures the information in the whole data. And then we go find the next most in an uncorrelated direction. In this case, we can explain almost 3/4 of the variability in our categorical variables with a single direction. The second most informative story explains only 5%, and then it drops off to nearly nothing. So we have definitely one pattern that's worth exploring, and we'll look at the second one as well. So the picture that you get when you ask for plot the output looks like this. All right. And we interpret this picture like we interpret a plot of principal components. If this was numerical data and we computed the first 2 principal components, plot them against each other, then looking horizontally from left to right, that speaks to patterns that explain that much of the story. And looking vertically tells us about patterns that explain that much of the story. By far, the biggest source of structure is what's shown horizontally in this picture, because it explains 72.6%. So let's look at what's happening horizontally. When you see levels of your categorical variables that are grouped close together, horizontally right now. Let's just focus on horizontally. Don't worry about where they are vertically. Horizontally, these points are grouped together. These points are kind of grouped together also. And the ones on the left are distinguished from the ones on the right. So the fact that these are all close together means that those levels of the categorical variables tend to occur together. There are a large proportion of the people in the data are between 30 and 45, are do-it-yourselfers, they live in a house, and they're not skilled or unskilled. So I guess they're magicians or something. I don't know what it is. Okay, so that tells you you found some structure in your data. There are people who tend to be of this type. There are also people over here, can't see all this because it got run off, but who rent, and this is probably, yes, apartment, who rent apartments. So there's a difference between people who own their homes, middle-aged, do-it-yourselfers, and people who rent, who tend to be a little bit younger. The age from 0 to 30 is closer to this group over here than it is to that group. Okay, that's what you essentially do with correspondence analysis. Throw it at the algorithm, or throw the algorithm at your categorical data. Take a look at proportions of variance explained. In this case, I see that there is something pretty substantial in the horizontal direction that we're going to be looking at. The second one is pretty mild relative to the first one. So I would say I'm going to base most of my interpretation on the horizontal direction in this picture. Secondary conclusions would be based on vertical, but I don't believe those quite as strongly because it's a much weaker pattern. If these were my data, I would report back, okay, we can distinguish at least two groups. There's these people and there's those people. So when you have, let's say, thousands and thousands of records, and you might have dozens of variables, making summary, simplistic pictures like this one, or the one that we saw with PCA, or the one we saw with clustering, helps you to visualize, what's in there. You could go in to the data and kind of reinforce or try to verify what we're seeing. Go tabulate how frequently do people fall into these categories. DIY, yes, age 30 to 45, tenure, own, and so on. You would see in the frequencies that you computed those tending to go together. Frequently seeing those things together. Not seeing these things together with those values as frequently. Okay. Correspondence analysis, it's for your categorical variables. Make the picture, interpret each direction in balance with the proportion of variance that it gives you. And then you're asking about which levels group together and which levels are different. All right. So that's it for exploratory stuff for now, okay? So you know some basic techniques to look at your data. What we're going to do with a lot of this class is statistical inference question.
What is dimension 1 in nature? Can you just interpret it like PCA?
Okay.
For example, PCA based on the collections of each of the founders, we could say that, okay, he's like something, an average of all the founders or something.
Okay, so the numbers question was about like what do these numbers mean? Where do these percentages come from? I'm not going to go into the detail of it. I can give you some resources. The big idea is that you construct a matrix of numbers. You need numbers in order to do this stuff. So the way that we get numbers is with something called a BERT table. It's an indicator matrix. Okay, so this is a individuals by variables matrix where the rows represent the individuals and the columns are dummy variables representing the categories. So a dummy variable for age, for example, we had 3 categories of age, less than 30, 30 to 45, 45 or older. We could construct separate columns, one column for young, and it's either 1 or 0 depending on whether you're 0 to 30. And then the next column is 0 or 1 depending on if you're 30 to 45 and so on. If you do that for the entire data set, all the rows, and then separate columns for dummies for every single level of your categorical variables, you have a matrix of numbers. And then essentially it does eigen stuff on that. Okay. So statistical inference. This is, I guess you could say that one of the primary reasons to learn statistics is to enable statistical inference. Inference is what we do when we have a sample from a population and there's a parameter in the population that we wish we could estimate. So we use our sample to estimate it and make statements about which we can say how confident we are. So let's imagine that there's a population of all individuals or items, plants, animals that we are interested in studying. So the population could be all postmenopausal women in the US, for example. In statistics, so there's inside the population, there is one or more parameters. So we could have a population mean, mu, the average survival time, or the average BMI of postmenopausal women in the US is mu. If we got every single one of them and computed their average BMI, we would know mu, and we wouldn't need statistics. There's a mean, and we might say there's a variance also. So let's say there's two parameters in this population, mu and sigma squared. In practice, we're stuck taking a sample. So this right here is the sample. Maybe there's some millions of postmenopausal women in the US. We randomly obtain 200 of them. So in, let's say, random sample of size n. Because it's a random sample, each of the individuals are viewed as independent of everybody else and identically distributed, which means they all came from the same distribution. Whatever the distribution is, they all came from it. So they all have the same population mean and variance. Let me just remind us, independent and identically distributed, IID. That's what we mean in this class by random sample. Okay. So things we could do on the basis of our sample. Let's say we have X1, BMI for woman 1 in our sample, X2, BMI for the second woman in our sample, XN. That's our data. Using our sample data, we have two population parameters. Mu and sigma squared. And we can have two corresponding sample statistics that we could use as estimates of those parameters. Statistics. In order to estimate a population mean, what we do is compute a sample mean. So add up those n numbers that we just got and divide by n. We call that x with a bar on top, x bar, sample mean. We can also compute a sample variance. This is what Stats 101 would call S squared. All right, so suppose we do this. We have maybe 100 women or 200 women that we sample. We can compute the average for them, the average BMI, x bar, and that's an estimate of the population mean. But just because it's an estimate, or estimates only are of fairly limited value. Because, let's say I ran this experiment or this study last week, and I randomly obtained 100 of these women. Based on my sample data, my 100 observations, I got an X bar of whatever, 20.4, and an S squared of 14. If you went and redid that experiment, you randomly sample 100 women from the population, and you compute your own mean and variance, yours are going to be different from mine, just because we will have wound up with randomly different people in our samples. But my sample is just as representative of the population as yours. So the issue when we want to talk with confidence about mu or sigma squared, population parameters, the issue is when we take samples, everything we see on the basis of the samples is random, subject to randomness. So what we say in statistics is that these sample statistics are themselves random variables. That means X bar has a distribution. S squared has a distribution. And you could think about if we were to go take samples of size 100 from this population, we could expect a distribution of X bar values, for example. We would see some that were really close to mu. Just by chance, we would see some that were bigger than mu. And just by chance, we'd see some that were less than mu. The hard part is, on the basis of our sample of 100 individuals, how can we say something with confidence about the value of mu? Things like confidence intervals and hypothesis tests are the primary way that we do that. Confidence interval would be, I saw 100 women, X bar was such and such, S squared was so and so. Based on that, I'm 95% confident that mu, whatever it is between these two numbers. I can construct an interval. I can also do a formal test. If mu equals 24, then the chance of seeing data like my 100 is less than 1 in 20. I could estimate that type of probability. And I could then make a decision. Do we think that BMI, average BMI is 24? Based on my data, if it was 24, I estimate the probability of seeing data like mine, or even more extreme, to be 0.05 or something. That's not very likely, which is a roundabout way of saying chances are we made the wrong assumption. That's a hypothesis test. Confidence intervals, hypothesis tests. Both of them require that we appropriately handle the fact that these things are random. So the way that we do that to do statistical inference, we require knowledge of the distribution of our statistics. Suppose we want to do inference on mu, the population mean. We could use X bar as our estimate of that, and then in order to be confident or have a stated level of confidence, we require what's called the sampling distribution of our statistic or statistics. Sampling distribution, all that means is a probability distribution for a statistic. Gets a special name. This type of probability distribution gets a special name to emphasize that it's for a statistic. Okay. So what we want is like that interval-based estimate that I mentioned, or the test that I mentioned. How do we do that? The first way we're going to learn how to do it is probably not the first way you learned it in Stats 101. We're going to use simulation to do inference. Let me show you what I mean. Statistical inference, there's several different flavors of inference. One is point estimation. That's what we do when we just compute a sample average. I have one estimate of the parameter of interest. I said that's of limited value because how confident are you in that estimate? I know your average from 100 women is not equal to the average of all the postmenopausal women. So just how close do you think your estimate is? That's where the confidence interval comes in, and also hypothesis test. So a confidence interval, it's a range of what we'll call plausible values for the parameter of interest. And we get to put a level, or we get to quantify how confident we are in our interval. I could be 100% confident that I know the average BMI of all postmenopausal women if I gave you a useless interval. I'm 100% confident that the average BMI of postmenopausal women in the US is between minus infinity and infinity. That's a perfect, nothing wrong with that statement. I will always be correct if I predict that you're between minus infinity and infinity, but that is not informative. So you would like to narrow that interval and get it down to something that's more practically useful. But as you narrow the interval, what do you think happens to your confidence? It's got nowhere to go but down. If I'm 100% confident, if I catch all possible possibilities, as I try to get more and more precise with my interval estimate, my confidence level has to go down. And then a hypothesis test is when we need to make a formal decision. Yes or no, is the average postmenopausal woman in the US obese? Which would be, is the average BMI bigger than whatever the obesity threshold is, 25 or something? Yes or no? And how confident are you in your decision? Okay. So the general strategy is that we compute a statistic. That's what I was mentioning on the whiteboard. There's a population, and there's a parameter that we are specifically interested in the population. We only have a sample. The way that we estimate the parameter is by computing an appropriate statistic. If I'm interested in the population mean, I would compute the sample mean. If I'm interested in the population median, I'd compute the sample median. Standard deviation, variance, interquartile range, anything you want to estimate, you would compute the analogous sample version of it. So once you have the statistic, you need to ask, what do I expect the distribution of my statistic to be? The sampling distribution of my statistic. If we can say, or at least approximate, the sampling distribution of our statistic, then confidence intervals and hypothesis tests will follow naturally. In particular, if you know the sampling distribution of, say, X bar, then a 95% confidence interval would be the values in that distribution that capture, or that within which is 95% of the probability. So suppose we could say, suppose the parameter of interest is mu, and the sampling distribution of our statistic, X bar, is like this. Centered at mu, we're going to see, with large sample sizes at least, it will tend to look symmetric and bell-shaped like this. Doesn't have to, but whatever it looks like, whatever the distribution, sampling distribution of X bar is, if you come over here and then go up to there, such that inside or in between the area underneath the curve, the probability, is 0.95. If you go to the left endpoint and the right endpoint that you have to get so that there's 95% in between them, that is called a 95% confidence interval. That's what a confidence interval is. So the reason that picture is on the screen is because if we can derive analytically or estimate via math or with our computer, one way or another, if we can get a picture of that sampling distribution, inference is right there. We can do inference. Hypothesis testing is similar. I'll draw a similar picture later on. But the key is we need sampling distributions. When we do a hypothesis test, I mentioned the general framework of that a moment ago. We're gonna try to decide, for example, is the average postmenopausal woman obese or not? Yes or no? We're working for the government, FDA maybe, and we're making decisions about public policy. So we need to make this decision, is the average above the obesity threshold? What we do when we do a hypothesis test is formulate the question into two competing hypotheses. The null hypothesis, which is the one that you would believe prior to somebody showing you evidence to the contrary. So if you're doing a research project, you set up the null hypothesis as the nothing to see here option. There's no information. The claim that I'm interested in is not apparently true. And the competitive hypothesis that you're interested in is called the alternative hypothesis. And you're asking, would it be unlikely for me to see data like I saw if that null hypothesis were true? If it would not be likely for me to see data like I saw when that assumption is true, then using like an inductive argument, you could say, I probably made the wrong assumption. That assumption's probably not right. What we do to actually put that into practice is we compute what's called a p-value. This is a probability, number between 0 and 1, and it is specifically the probability of seeing data like yours, or we will say even more extreme, if the null hypothesis is true. And if the p-value then is small, sufficiently small, that's an indication the null hypothesis probably is not true. It would not be likely to see what you saw if the null were true. We compute a p-value, and if it's less than some threshold, we reject the null hypothesis. If it's not, then we say we didn't have enough evidence to reject the null. We failed to reject. How do we get sampling distributions? If you have a fully specified probability model, then you might be able to mathematically derive what the sampling distributions are. There are some cases where it's straightforward. Other times, there are asymptotic results that say, like for example, the sample mean. If the sample size is large enough, then the sampling distribution of X bar looks like this. It's bell-shaped, normally distributed, centered at the truth. When you have a large sample size, we often have some nice limiting results that we can use to approximate sampling distributions. And the strategy that's a little bit more modern that I want to introduce you all to is the simulation-based way to approximate sampling distributions. Back here, the red curve, I'm saying, is the sampling distribution of X bar. So suppose that was normal and we knew or could estimate its parameters. If it was normal, then you could get these percentiles that you need for the confidence interval, for example, really easily. You could just go to R and ask for the appropriate percentiles from a normal. An alternative to being able to say the curve, the function that defines the curve is such and such, therefore it's a normal random variable, an alternative would be if we could sample from this distribution. So if there was a way for us to simulate an X bar. Here's one X bar that I simulated by essentially simulating a sample from the population like ours, and then recomputing X bar. Here's another X bar, and suppose we did this lots of times, 1,000 times or something. If you drew a histogram of these simulated X bars, you'd have, a rougher looking but still appropriate picture of a distribution. And it turns out that you can use this simulated distribution just like you would have used this one, and still be able to do valid statistical inference. So what we're going to learn in this topic this week is how to simulate one of these sampling distributions. So second bullet point, or third bullet point, if we can somehow draw samples from the sampling distribution, it's almost like we know the distribution itself. We may not know the function that defines it analytically, but if we have a big pile of samples from it, it's like we know it anyway. The main resampling or sampling technique that I'm going to teach you for doing this, that's extremely flexible. It applies when we get to regression. It applies when we get to correlated data regression, survival analysis. It's a non-parametric way to enable statistical inference in very general settings. It's called the bootstrap. And the idea is that for each of many times, capital B, we take our original data, so suppose we had those 100 postmenopausal women. What we're going to do is sample with replacement from them, with replacement. So line up the 100 women and randomly pick one. So woman 14 is now in my little sample, the beginning of my sample. Then you put that person back. We have 1 to 100 again, and you randomly pick again. Suppose we got person 82. Put them back. Resample again. Maybe we got 14 again. That's okay. We do that 100 times. Now we have a new sample of 100 BMI measurements. It seems like we're cheating because we're just resampling from our original data. That's the idea of bootstrap. Bootstrap is like pulling yourself up off the ground with your own bootstraps. Not really possible to do that. So it's got this kind of magical feel to it because all we're doing is taking our observed sample and sampling with replacement from it to create like a new one, a new pseudo sample just like ours. We're trying to make this happen. Based on my 100 numbers, I could compute X bar. But I need to know what does X bar tend to look like on repeat sampling. And the way we do that, sample with replacement from the data, that's a new pseudo sample, and now compute X bar again. So there's a new X bar. Redo the whole thing, sample with replacement 100 times, there's a new X bar, and so on. And if we do this lots of times, we're going to have a picture like this one. All right, so for capital B times, we're going to use a for loop in R. I'll give you plenty of examples of how to do that. You go inside and sample with replacement to get a new pseudo version of your data, and then you compute the statistic that we're interested in. If I'm trying to do inference on a population mean, then my statistic is X bar, the sample mean. Each time I sample with replacement, I record the X bar that resulted. After doing that, we have capital B simulated versions of our statistic. These, if we make a histogram, for example, would approximate the sampling distribution of X bar. And then to get a confidence interval, we'll end with this. To get a confidence interval, let's say you want a a 95% confidence interval or a 90%, 99%. In general, we're going to say 100 times 1 minus alpha percent, where alpha is some small number. If I wanted a 95% confidence interval, I would say alpha equals 0.05, for example. But by writing it this way, it's more general. So suppose you want the 100 times 1 minus alpha percent confidence interval for a parameter. In the binomial case, the parameter would be p, the probability of success on any one trial. Or it could be x bar, or mu in the continuous case. The way you do it is you bootstrap, step 1, to obtain capital B pseudo versions or simulated versions of your statistic. And then to get the actual confidence interval, you get the alpha over 2 and 1 minus alpha over 2 percentiles of those simulated statistics. If I want 95% confidence, I'm going to get the 2.5th percentile and the 97.5th percentile. That's going to be doing this kind of thing with the blue line segments, blue vertical line segments here. This would be, say, the 2.5th percentile, 2.5% of the area under the curve is to the left. And this is the 97.5th percentile. 97.5% is to the left, which means 2.5% is to the right. Those two numbers, you could write them down and correctly call them 95% confidence interval. Let me just end with this picture right here. This picture is a way that you can interpret or understand what confidence intervals are doing. This is a simulation. Simulation is where you set up a probability model and you generate random numbers from it. Since you set up the probability model, you know the truth. You know the answers to its parameters and stuff. So then you can simulate, create a random sample, and do something, simulate again, do the same thing, and repeat doing that. And by looking at what happened over those repeat simulations, you learn about the operating characteristics of whatever technique you're using. This is a simulation where for each of thousands of times, I only show you 100 here, but for each of thousands of times, I randomly generated some data. These were binomial data in this case. P was equal to I forgot what it was, but it was right there. That was the true parameter value. And on the basis of one sample, let's say we took a sample of 100 observations from this population. And this topmost green line represents the confidence interval, the 95% confidence interval that we would have got from that one sample. We got a sample of size 100 from the population. We used that sample to get an estimate and then a confidence interval via, say, the bootstrap. Sample with replacement, get those percentiles, and then that topmost horizontal green goes from left endpoint to right endpoint. Those left and right endpoints are the confidence interval. That topmost green segment overlaps with the vertical dashed line segments. Those are located at the truth. That's the true parameter value. So the topmost interval contained the truth. That's why it's colored green. All those intervals that are colored green were, quote, correct, or they captured the truth. But notice that there are red ones too. For a 95% confidence interval, the way you get to interpret is 95% of the time, whenever you get a sample and apply this stuff to get what we call a 95% confidence interval, 95% of the time you will have captured the truth. But 5% of the time you will have not. And in practice, you don't get to know which of those which camp you're in. You probably contain the truth, but you can't deny the possibility that you're one of the unlucky 5%. So imagine going to New England Journal of Medicine, flipping through the last 20 years of papers, p-value after p-value after p-value, confidence interval after confidence interval after confidence interval. What you could say is, I expect 5% of these to be incorrect. I say the average BMI goes between 22 and 26, and I'm totally wrong. It's not in there, even though I'm, quote, 95% confident. Okay, questions? We'll keep filling in the pictures on inference, and I'll show you some examples next time in how to do the bootstrap and how to actually get one of these intervals. Okay?